Hello and welcome. We're going to continue with chapter 27, Charged Particles, part 2. We're going to now look at the deflection of a charged particle through an electric field. So I'm here on O Physics. They've got a simulation that is called Charged Particle in the Electric Field, and we're going to look at a charged particle in the electric field. So we've got the positive field at the top, negative field at the bottom. The field strength is 1000 newtons per coulomb, and we've got the velocity as 5000 meters per second. Okay, and it goes much slower than 5000 meters per second, but we see here a curve upwards. Okay, and if we think about that, the reason that it curves upwards is because the object has a charge. It curves towards the negative side, so that object has to be positively charged. Okay, so if we think in terms of voltage, same thing. Okay, we can either have the electric field or we can have the voltage. We can swap the field around, and if we run, then we're going to see it's going to go to the opposite side. Okay, if we increase the this velocity, we're going to see the object moves a bit further, but it still hits the floor. So there's a few things that we can look at. We can look at the charge of the particle. If we decrease the charge of the particle, okay, we can take it closer to 0. Let's make it 1. Then we'll see it will deflect less because it has less of an effect. And then we can also make the particle's charge the opposite direction. So now it's a negative charge, so it's going to deflect upwards. Okay, and we can also determine the particle's mass. The lighter the particle is, what do you think is going to happen? It's going to happen. The force on it is going to have a bigger effect, and the heavier the particle is, the less the deflection would be. So there's a few things that we can look at here and at which we can calculate. So let's look at some formulas here. So if we can remember here, we divided it into vertical and horizontal in AS, and we said that the horizontal velocity is equal to displacement over time because it's not accelerating horizontally or decelerating. Vertically, we're going to use UVAST, and because the initial velocity is 0, S is half AT squared. Okay, and we know that the times are the same. If we think in terms of forces now, vertically, we know that the electrostatic force is also the force causing it to accelerate. It's the resultant force. So if we combine these two equations, we get that the acceleration is the charge of the plates, of the field, the charge of the plates divided by the mass of the particle. Now, if we say T is equal to S over V, and we substitute all of that into our equation, we end up with the following, that the distance between the plates is half, okay, which becomes 2 at the bottom, E Q M, and then T squared, so it's going to be S squared V squared. Now if we look at this, this is the velocity, that's the displacement. So you would think that this S and that S is the same, but let's think in terms of vertical, so that's the Y displacement, and let's think in terms of horizontal, that's the X displacement. So we've got X squared over Y. Okay, so we've got the field, which we can control, the charge, we choose the charge that we have, and the mass, and the velocity can be determined. We can do all of those inside. So we are left with basically a relationship, and we can see that the Y displacement is directly proportional to the X squared, which gives off the parabolic movement, or basically which the shape of a parabola or half a parabola. Okay, so this is just a few equations to do this. If we look at the simulation, we can control those four, and basically we are looking at the displacements vertically and horizontally and the relationship between the two. Now obviously, if we want to calculate every time we change some of these values, our y displacement and our x displacement changes. Our y displacement is just that half, it's how far it travels horizontally that we are sometimes concerned about. Next we will start looking at deflection through a magnetic field. So once again we're on O physics, and we see that we can also use a charged particle through a magnetic field, and this is where this chapter that we're busy with comes into play. We're going to be using Fleming's left-hand rule. So if we start and we show our particle, we see the curved path. Okay, if we look at the charge, it's a positive charge, so I'm going to use the positive way, the normal way of FBI. Okay, the direction of the current will be your middle finger, so quickly get your FBI ready. Your middle finger points towards the direction of the flow of the particle. Your index finger points outward, so you twist your hand with your wrist towards your screen, and then you will see that your thumb points downwards. If we increase or change the charge to a negative charge, now we flip around our using the other FBI, the one that messed up everything. Okay, and now we point our middle finger in the direction of the charge, okay, which is now in the, like a very bad sign. Okay, and you put your index finger out of the page towards you, and then you are calculating the field upwards. So just a quick demonstration of how that would look like. Now once again, if we look here, we can determine the mass of the particle. So the heavier the particle is, according to our we can determine the mass of the particle. Okay, the heavier the particle, we have to know what the result is going to be. We're going to look at the forces, the one with centripetal force, the mass, the velocity, the charge, and the field strength. So the field strength, the more lines, field lines coming out of the page, or less. Okay, and there's a negative field strength when it goes into the page, out of the page, into the page. So if we do the field the other way around, it deflects upwards. We've got a positive charge, so we use our normal FBI, and if we point our gun into the field and we point our middle finger where the trace goes, the force deflects upwards. So as we've seen yesterday, the mass is equal to the radius is equal to the mass, the velocity, the field, and the charge of the particle. So the relationship would be, remember, the radius of the circle, or how much it would curve, depends on how heavy the object is. The heavier the object, the more the radius would be. The faster the object, the more the bigger the radius would be. So a bigger circle or a longer curve. The stronger the magnetic field is, the shorter the radius would be, so the quicker it turns, and the bigger the charge of the particle is. Now remember, if you compare a alpha particle with a charge of 2+ to just a normal 1+ particle, then we're going to have, but the moment we compare it to a -1, then we flip our normal FBI to the other FBI. So it will also have, the charge also has a directional effect. So the other three don't determine the direction of Okay, this determines direction, whether it is into the board or whether it is out of the board. Okay, and then the charge will determine whether we use our fingers like this. The force is going to be the direction of this this curve. So those would just determine the size of the curve, okay, whether it's going to be a big curve or a small curve. These also determine the size of the curve, but they've also got a directional influence, whether we're going into the page, whether we're coming out of the page, whether we're using the current this way or whether we're using the current this way. Okay, so that's all affected by that formula. So next we will be looking at what happens when we combine electric and magnetic fields. So if we combine these fields, we're looking into a probe, okay? We know that if I shoot a particle coming, let's say, out of the board here, if it's a charged particle, it can be deflected upwards or downwards depending on the size or the charge and the size. But because it's a charged particle, there's a magnetic field as well, and the charged particle can either deflect towards the south or towards the north using Fleming's right-hand rule. So if we're looking at the current, that's the direction of the magnetic field. Okay, if it's a positive charge, the force is going to be up. If it's a negative charge, it's this way around, so that's south, out of the page, then can be down. So this field, the electric field, has a up-down motion, and because our magnetic field and our flow of charge is perpendicular to each other, the field, the magnetic field also has an up-down effect on our charged particle. So if we shoot that particle straight through the middle, okay, that means the following. So let's make this an electron, and let's rather say it goes into the field just to make our thing a bit easier. If it comes straight out, okay, right in the middle through these plates, that means that the B field is equal to the electrostatic field. Okay, so what will be the effect on an electron in an electrostatic field? The electrostatic field will want to make it go up. Let's think what the effect on an electron will be. Remember, it's an electron, so we swap around. The field is going, the electron field is from north to south. The electron is going out of into the page, okay, and so for this setup to work, I've swapped these two sides around the wrong way. So they set it up specifically so that if we take our, let's just swap it the other way again, and we make our positive and negative the opposite way. So the electric field is going to push it down, and if we now we're shooting towards the south, it goes in, and then the magnetic field is upwards. Okay, so if the electric field wins, it deflects downwards. The magnetic field wins, it deflects upwards. And if they're equal, it's going to come right out of the middle. So when the magnetic field, so if we just look at the equation, this is going to be BQV, and the electric field is Q times E, which is the charge. The Q's cancel, that's the velocity there. So we get that the velocity is equal to the electric field strength over the magnetic field strength. So when my velocity comes right through the middle, when there's no deflection, that means the two fields are equal, so this relationship will be true. Okay? When the magnetic field is bigger than, okay, bigger than, we're going to have V is bigger than E over B, and it's going to deflect towards the negative side, the same direction as the charge of the object, or the same to the same charge. So it's negative to the negative if the magnetic field wins. If the electric field wins, okay, let me just make it green. Then the deflection is going to be according to where the electric field wants to push it. So then it's going to deflect downwards. Okay, and then the velocity is less than that relationship because the magnetic field is bigger than the electric field is bigger than the magnetic field. So in your textbook, we will see the part of a velocity selector. This is how we build a velocity selector, and that we make sure that the velocity that comes through of that particle is of a specific velocity. So we can control, using a type of velocity gun, that we can control the velocity at which the electrons or the alpha particles also comes through. Otherwise, we don't have any control. Remember, we use velocity selection in a few other medical applications as well. I hope that slightly makes sense. I want you to read through the next few pages in the textbook, and then we can discuss it again. Thank you.